Suppose a yo-yo has a center shaft that is 0.8 centimeters in radius. I'm going to call that R1 right there. And the outer edge of the yo-yo has a radius of 2.9 centimeters. So we can kind of draw that like that. We'll call that R2. The mass of the yo-yo is 70 grams, and its moment of inertia around a rotational axis through its center, parallel to the shaft, is 2.35 times 10 to the minus 5 kilogram meter squared. It rests on a horizontal surface and is being pulled to the left by a horizontal string with a tension of 0.25 newtons. The string does not slip in the center shaft, and the yo-yo rolls without slipping on the horizontal surface. So just really quickly here, I can draw the forces. There's going to be a force of gravity acting down, mg. There's going to be a normal force acting up. If you're pulling it to the left, there's probably a friction, static friction on the bottom point to the right. And of course, it's the tension acting to the left. And question A says, which direction, clockwise or counterclockwise, does the yo-yo rotate? To determine this, conceptually, we can consider the pivot to be at the bottom, which sort of looks like this. Here's the pivot, here's that shaft, here's tension. So that this way, gravity, normal force, and static friction all give zero torque around this bottom point. So you can see that the normal force and the friction force act at that bottom point, so they can't have any torque if they act at the pivot. And then the gravity force acts along a force line that goes through that pivot as well. So it can't have any torque. So the only torque here comes from tension, and this is counterclockwise. So to sum up, there's only 4 forces. If I choose the pivot at the bottom, only one of those forces gives a torque, and that torque is counterclockwise, so the yo-yo will rotate counterclockwise. If I had considered the pivot point to be at the center of the yo-yo, as you normally would, the problem there is that, so normal force and gravity would still have zero torque, but now you have a torque from static friction and an opposite torque from tension, and it's not clear which is bigger, so you'd have to work it out to figure out. But you would also figure out, if you did it properly, net torque was counterclockwise even in that case, so the yo-yo would still rotate counterclockwise. So that leads us to part B, which asks what is the acceleration of the center of mass of the yo-yo as it rolls. So to do this, now let's choose the pivot at the center of mass of the yo-yo. Since we know the rotational inertia around that point, it's given. Let's draw the extended free body diagram and make a list of our knowns and unknowns. Pivot. Okay, so we've got Fs to the right. We've got normal acting up. We've got gravity, mg, acting down, and we've got this tension acting to the left right there. Make a list of our knowns. We have that R1, this distance, is equal to 0.8 centimeters, so I'll call that times 10 to the minus 2 meters. R2, this outer radius, is 2.9 centimeters, or times 10 to the minus 2 meters. The mass of the yo-yo was given as 70 grams, so I'll call that 70 times 10 to the minus 3 kilograms, again converting to SI. And the rotational inertia, or moment of inertia, is 2.35 times 10 to the minus 5 kilograms meters squared. And the tension, pulling it to the left there, is 0.25 newtons. And we will define y to be up, x to be the left to the left in this case, because I think the whole thing's going to roll to the left, and I'm going to define positive angular acceleration as being counterclockwise, since I think it is going to rotate counterclockwise, and that's a good historical convention. So those are the knowns. The unknowns in this problem are, we don't know Fs, the static friction of the floor and the bottom of the yo-yo. We don't know acceleration, which is going to be R2 times alpha. This is the linear acceleration of the yo-yo, and I've used R2 as being the outer radius, so this is where it's rolling without slipping. And in fact, we're asked to find this, so that's an important unknown to keep track of. Alpha, which is the net torque divided by the rotational inertia, is Newton's second law for rotation. This is the angular acceleration of the yo-yo. We don't know that. but we can probably find it. Don't forget that the torques from mg and also the normal force are 0. So the net torque, alpha, we can find this, is going to be from the tension, actually pulling it clockwise around the center point at a distance r1. So clockwise is negative, the tension times r1, and then the static friction pushing it counterclockwise with a distance r2. So counterclockwise is positive, static friction times r2 divided by rotational inertia. We're going to call that equation 1. So that's utilizing Newton's second law for rotation. What about just Newton's second law of linear? Okay, so recall that there's only 4 forces acting on this thing. So we've got F net in the y direction is equal to 0, because it's not accelerating up or down. That's going to be the normal force is acting up, minus mg is acting down, 0, so this just means that n equals mg. Actually, that's pretty useless. But here's an important equation. F net in the x direction is going to be the mass times the acceleration. And that acceleration is linked to the angular acceleration by this rolling without slipping constraint. And remember I've defined x to be towards the left, is going to be the tension minus the static friction. Tension minus static friction. So this allows us to solve for static friction. Static friction is equal to the tension minus m times a. So I can take this and I can plug this into 1 so that I get alpha is equal to, let's rearrange this a little bit, static friction, tension minus ma times r2 minus tension times r1, all divided by I. And then also recall that this alpha is equal to the acceleration divided by r2 for rolling without slipping. So the acceleration divided by r2 is equal to, let's actually multiply through this parenthesis, tension times r2 minus m times a times r2 minus t times r1, all divided by I. I'm trying to find a here, so this is going pretty well. Let's just, we're going to multiply both sides by I, multiply both sides by r2, so we get I times a is equal to t times r2 squared minus m times a times r2 squared minus t times r1 times r2. And we'll just solve for a. We have to collect all the terms that have a in them on the left side of the equation. So I get I times a plus m times r2 squared times a is equal to, and then all the terms that don't have a in them on the right hand side of the equation, t r2 squared minus t r1 r2. Okay, so now I can pull out the factor of a. I've got a times I plus m times r2 squared is equal to, it's actually, you can pull out the t times r2 is in both of those terms, times r2 minus r1. Divide to get a is equal to t times r2 minus r1 divided by I plus m times r2 squared. So let's put all of our numbers in here. You got 0.25 is the tension, times 2.9 times 10 to the minus 2 is r2, times 2.9 minus 0.8, and I'll just multiply all that, times 10 to the minus 2, divided by, on the bottom we have the rotational inertia, 2.35 times 10 to the minus 5, plus the mass, which is 70 grams, times r2 squared, 2.9 times 10 to the minus 2, all squared. Let's actually start with the 2.9 minus 0.8. It's 2.1, so 2.1 times 10 to the minus 2 times 0.25 times 2.9 times 10 to the minus 2. It's a small number, and then you divide it by, open parentheses, 2.35 times 10 to the minus 5 plus another open parentheses 70 grams times 10 to the minus 3 times 2.9 times 10 to the minus 2 squared, and parenthesis equals 1.85 meters per second squared. That's the acceleration of the yo-yo. Two disks are cut from the same uniform board. The radius of disk B is twice the radius of disk A. The disks can rotate around axes with negligible friction. These are vertical axes, I guess. Two very light battery-powered fans are attached to the disks as shown and exert forces. The fan on disk B is more powerful, so that FB is 2FA. What is the angular acceleration of disk A, alpha A, in terms of that of disk B? The alpha A equals alpha B. Then there's twice, 4 times to 8 times or 16 times. I see. Well, yeah, so the basic equation is Newton's second law for rotation, which is that alpha is equal to the torque, the net torque, I guess, divided by I. And these are disks, and the disk equation is that I is equal to 1/2 mr squared. I think there's some probably fancy way of doing this with ratios, but what I am going to do is just solve the alpha for disk A, solve for disk B, and then compare them. If I don't know something, I'll just write down a letter for it. So actually, we don't know the masses, which is sort of interesting. The mass of a disk depends on surface area. It says that they're cut from the same uniform board. What that means is that they have the same, I guess, surface area density or something. I'm going to call that sigma, mass per area. I don't know what it is, but I've defined it now. So what this means is that the mass of A is ma is equal to sigma times its surface area, which will be pi times r squared. And the mass of B is going to be sigma times 2r squared, which is going to be 4 sigma pi r squared. So this one's going to have 4 times the mass. So that's sort of interesting. But yeah, let's just work this out. We know that alpha A is equal to the torque on A divided by I sub A. Now the torque is going to be equal to FA times the radius, because it's a perpendicular force, divided by IA, which is going to be 1/2 MA times, and its actual R, which is R squared. So that's going to be equal to F, one of these R's will cancel the squared down there, FA, there's the 2, which will come up from that half, and MA is going to be sigma pi R squared, and there's another R on the bottom. So it is 2 times FA divided by sigma pi R cubed. Okay, good. And then alpha B is equal to its torque on it divided by I sub B. So this is going to be equal to FB times, now looking at that, it's 2R is the distance, the lever arm there. So I'll put a 2R up there. Divided by 1/2 MB times its 2R squared. That's the rotational inertia for a disk there. This 2, bringing up the 2, we've got a 4 FB times R divided by MB, which is 4 sigma pi R squared, times 4 times R squared. This R cancels one of these squareds in the bottom. 4 cancels one of the 4's in the bottom. We get FB divided by sigma pi, oh, there's a 4 down here still, from this one, times R cubed. So now we can kind of, oh, there's one more thing. FB is equal to 2FA. So it's equal to 2 FA divided by 4 sigma pi r cubed. So the 2 makes this a 2 on the bottom. So it's FA divided by 2 sigma pi r cubed. So alpha A is equal to 4 times FA over 2 sigma pi r cubed, right? If I just pull out a 4 divided by 2 is 2, so that'll be the same. This is the same as everything that's in there, so it's equal to 4 times alpha B. So the answer is C. Okay, a frictionless pulley has the shape of a uniform solid disk, I is 1/2 mr squared, of mass 2.5 kilograms. Let's put that, start listing our unknowns here. And radius 20 centimeters. I'm going to call that 0.2 meters. A very light wire is wrapped around the rim of the pulley, and a mass M2 equals 1.0 kilograms is hanging from the bottom of the wire. The system is released so that the pulley rotates counterclockwise as the hanging mass accelerates downwards. What is the magnitude of the acceleration of the hanging mass? A is what we're trying to find. So here's our, basically this tension is going to be pulling down on the pulley, and tension is going to be the same tension we'll be pulling up on the hanging mass. So we're going to need 2 free body diagrams. The pulley force diagram will give us a Newton's second law for rotation. So it looks something like this. You've got tension acting downwards at a distance r from the axis, and I don't think there's anything else that's going to produce torque. Presumably you have an upward normal force on the axis, and you've got gravity pulling downwards at the axis, but those don't produce a torque. So the Newton's second law is alpha is the net torque divided by I is just going to be tension times R divided by I. And just so there's no confusion, I'm going to change the little r's to capital R here because it was a capital R there. So sort of rearranging this, I've got T times R is equal to I times alpha. Okay, so that's one equation. Another one is the hanging mass force diagram. The mass has got M2G is the force of gravity pulling downwards, and the tension force is pulling upwards, and it accelerates downwards. So the acceleration downwards, define plus is down here, because I know it's accelerating down, is going to be the net force in the downward direction divided by M2, the mass of that hanging mass. So that's going to be, now the gravity is pulling in the forward direction because I have defined plus is down, M2G minus the tension is keeping it, is pulling upwards or in the negative direction. So rearranging, I've got M2 times G minus T is equal to M2 times A. Okay, so that's another equation. And there's one more equation that relates things. This is the, I sometimes call it the acceleration constraint. Here, you've got the angular acceleration of the pulley and the linear acceleration of that hanging mass, but they're connected because the string doesn't slip on the pulley. If the pulley rotates a certain angle, the string will go down by that angle in radians multiplied times the radius of the pulley, and the velocity and acceleration will go the same way. So basically, the acceleration is equal to angular acceleration in radians per second squared is equal to the linear acceleration divided by r. So that's this acceleration constraint. We can even, and now we can start plugging these things in. We're going to solve for A here, which is what we really want. So we can eliminate alpha by plugging it in there. So I've got T times R is equal to I times A over R. So we can solve for tension, which we don't know here. It's going to be I times A divided by R squared. So I can take this and plug that into here, because this all has A's in it and things we know. We don't know tension, we didn't know alpha, so we're getting rid of, anytime we have a variable that we don't know, we plug it into some other equation to kind of get rid of it, right? So now I've got M2 times G minus I times A divided by R squared equals M2 times A. We're going to solve this for A, so gather all the terms with A on one side of the equation. Add M2A plus I over r squared. A is equal to m2g. Pull out the factor of a there. A times m2 plus I over r squared is equal to m2 times g. So A is equal to m2 times g divided by m2 plus I over r squared. And recall that I is equal to m, 1/2 m r squared, right? Over 2. So I over r squared is equal to m over 2. Just plug that in right there. So you get the acceleration is m2 times g divided by m2 plus m over 2. So we can plug in numbers for this now. M2 was 1 kilogram times 9.8 divided by 1 kilogram plus, the pulley was 2.5 kilograms, so 2.5 divided by 2, which is 1.25. So that's 9.8 divided by 2.25 is 4.36 meters per second squared. Okay, door A is 2 meters high and 1 meter wide and made of light fiber with a steel frame. The mass of the fiber is negligible. The uniform steel frame goes around the perimeter of the door, thick black line, and has a total mass of 6 kilograms. And it looks like, there's the picture. And door B is also 2 meters high and 1 meter wide and has a mass of 6 kilograms, same as door A. However, door B is made of solid wood and so has a uniform density. Which door has the larger rotational inertia? A, B, or they have the same? Well, yeah. I don't really know any quick way of doing this, but I think we can just figure it out. Door B is the easier one. So let's start with door B. It seems to be kind of like a slab, a rectangular solid, rotated around one edge. And unfortunately, this is not in the table of a figure 10.11. So we can search it up. I Googled on rotational inertia of slab rotated around edge, and it gave this following image. A plane or a slab about the edge is 1/3 ma squared, where a is this distance that's going away from the rotation axis, which I think in our case is going to be the 1 meter there. So I'll just note, this is similar to rod about axis through one end perpendicular to the length. That's where you had a rotation axis and a rod where the mass went away from there and you're twisting around that one edge. So that's the same equation as for this one, sort of the same distribution away from that axis. So what we can do is for IB, the rotational inertia of door B, just use 1/3 m times a squared equals 1/3 times 6 kilograms. A is 1 meter in this case, so 1 meter all squared. 6 divided by 3 is 2 kilograms meters squared. Okay, so that was the easier of the two. The harder one is going to be door A, but it can be broken into four masses, all steel rods. So very thin, narrow, long rods. I'll draw it as this one, this one, this one, and this one. We'll just call them M1, M2, M3, and M4. And we know that the sum of these all is 6 kilograms. And it also seems to me like M1 and M3 are 2 times M2 and M4. Does that make sense? Anyway, there's 6 of them, and if you count M1 and M3 double, and it's 6 kilograms. So I think M2 equals M4 equals 1 kilogram, and M1 equals M3 equals 2 kilograms, twice as much. So 1 plus 1 plus 2 plus 2 is 6 kilograms. So that's good. Okay, and so then there's the rotation axis, which I can draw up this left end like that. So M1 is on the axis. It's just twisting around. So what that means, every particle in M1 is a distance r equals 0 from the axis. And remember, for a particle, that I, I'm going to call this I1, is equal to m1 times r squared. If all the particles are the same distance r, you can just use that equation for particles, and so it's 0. And in fact, let's do m3, same thing. If this is the distance r here, then for m3, every particle is 1 meter from the axis. That's its r. So we'll use I3 is equal to m3 times r squared is going to be, it's 2 kilograms, and all the particles are a distance 1 meter, so you put 1 meter squared, just mr squared. There's no fraction if all the particles in an object are the same distance from the rotation axis. So actually that's just going to be 2 kilograms meters squared, which actually I think was the answer for IB. So even if M2 and M4 have any kind of contribution, I can already tell you that door A is going to have the larger, so I think the answer is A. But why don't we just work this out again for completeness. So M2 and M3 are this thin rod about axis through one end perpendicular to length from figure 10.11 in your textbook. And so it's just I is equal to I2, I guess, is M2 times L squared over 3. And L is this, again, 1 meter. So it's 1 kilogram times 1 meter squared divided by 3. It's just a third of a kilogram meter squared. And I4 on the bottom there is the same thing, 1/3 kilogram meters squared. And so for door A here, IA is equal to I1 plus I2 plus I3 plus I4. So it's 0 for the left, plus a third for the top bar, plus 2 for that far bar, that's where most of the rotational inertia is, and plus a third for the bottom bar. And you get 2 and 2/3 equals 2.67 kilograms meters squared, which is greater than the 2 for door B. So the answer is door A. Okay, a basketball rolls without slipping down an incline of 15 degrees below the horizontal. I mean, there's no diagram, so let's draw one. So let's draw an incline and put the 15 degrees there, and draw a basketball. And it's rolling down the incline, kind of like that. Clockwise rolling, and it's going down that way. The basketball has a mass of 0.363 kilograms and a radius of 0.12 meters. What is the magnitude of the force of friction on the ball as it rolls? Treat the basketball as a hollow sphere with a thin wall. Yeah, so the idea here, I guess, is it's accelerating down the incline. So if it started from rest and started speeding up down the incline, it would have a tendency to want to slide down. So there must be a force of static friction to roll without slipping. Static friction must act on the bottom and get it rotating clockwise, right? So if I want to draw it in red here, this force to turn it clockwise actually has to be up the hill. I'll call that F sub S. Okay, and that's what we're trying to find. Okay, so, and I guess we can also write down a few things. The knowns here are that the mass is equal to 0.63 kilograms. The radius is 0.12 meters. We can find from figure 10.11, there's actually a thin spherical shell about any diameter. I guess you could sort of think of as the ball is rolling, the center of the ball is the rotation axis. So you've got I is equal to 2mr squared divided by 3. Now we're going to need sort of a force diagram here. So let's draw one, force diagram. It's just going to be that same ball, but let's draw all the forces we know are acting on it. So here's the ball, and tangent to the edge of it, here's this static friction force that we're trying to find. I guess perpendicular to the static friction and towards this rotation axis will be the normal force. Acting on the center of mass, which is this empty spot in the very middle, there's going to be mg, the gravity force acting downwards. And I guess that's it, right? It's only one point of contact with the floor. So, I guess what we're going to do is solve Newton's second law. So we need to do the x and y axes. So I think probably the easiest thing will be to tilt the axes. Y will be perpendicular, and x will be along incline. The normal force is along y. And then we will make clockwise also define a rotation positive. So what's going to happen here is that it will, AX is positive. It'll roll in the plus x direction. And alpha is positive. And the rolling without slipping acceleration constraint, it's always the same. It's alpha is acceleration divided by r. In this case, it's a sub x. So that's going to be an important equation. Call that equation 1, I guess. Newton's second law, let's go along x, because that seems to be the important thing, is that the sum of all the forces in the x direction is the mass times acceleration in the x direction. So what do we have? We have the normal force doesn't contribute. So let's actually just list them. It's going to be Fs in the x direction plus the normal force in the x direction plus mg in the x direction. So that's going to be negative Fs, because it's backwards, plus 0, because the normal force is just perpendicular to the surface, and we've defined that to be y. And so this is now where we're going to have to decompose the gravity force into its two components. So if there's a right angle there, if this is mg, this is going to be mg in the x direction. This is going to be negative mg in the y direction. And the angles here, this is going to be your 15 degrees right here. So for that force, I would say that sine of 15 degrees is equal to the opposite divided by the hypotenuse, mg in the x direction divided by mg. So that means that mg in the x direction is equal to mg sine of 15 degrees. Sort of makes sense, right? If you were to reduce the slope down to 0, then there should be no gravity component in the x direction. So you need a sine, not a cos. So plus, so this is in the forward direction, mg sine 15 degrees. That's the sum of the forces. It equals to m times a. So just getting rid of the 0 here, negative Fs plus mg sine 15 degrees is equal to m times a. We're going to call that equation 2 for now. And it's got an Fs in it, which is what we're trying to get, so that's good. And then let's do Newton's second law for rotation around the center of mass. Very simple. It's the sum of all the torques is equal to rotational inertia times alpha. So the normal force only acts towards the axis, and mg is on the axis, so the only force providing any torque around that center of mass is the static friction, is Fs. And it's at this distance r. So Fs times r, and that's in the clockwise direction, so it's positive, is equal to, it'll be a third the mass times r squared. That's for that, it's 2/3 for the thin spherical shell, times alpha. Okay, so this is equation 3. I'm not going to use Newton's law in the y direction. The forces just there should balance. The normal force should balance with mg cos theta, I guess, but I don't think that matters. We don't care about the normal force. So the 3 unknowns here that we care about are Fs, acceleration, and alpha. So we're going to eliminate a and alpha and solve for Fs. using those three equations, three unknowns, right? So first step, we have an equation for alpha, which we could plug in to, I guess, this equation 3, since it has an alpha in it, and then solve for a and plug it into equation 2. So let's plug 1 into 3. You get Fs times r is equal to 2/3 mr squared times a divided by r. This squared cancels with that r. Divide both sides by r, which is kind of funny. So you get Fs is equal to m times a times 2 divided by 3. So a is equal to 3 static friction divided by 2 times m. We don't want to solve for Fs because we're trying to solve Ss. Now we're going to take this and plug it into equation 2. So equation 2 is that negative Fs plus mg sine 15 is equal to m times a. So it's equal to m times 3Fs divided by 2m. M's cancel. We're trying to solve for Fs, so gather the terms of Fs on one side of the equation. Mg times sine of 15 degrees is equal to 3Fs over 2 plus Fs, which is 2 over 2, so it's going to be equal to, I guess, 5 over 2 Fs. So that means that Fs is equal to 2/5 mg sine of 15 degrees. So 2 over 5 times the mass is 0.63 kilograms times 9.8 meters per second squared is g times sine of 15. So the radius of the basketball doesn't matter for some reason. I get Fs is equal to 0.64. And the answer is in newtons.